hence we think that the escape rates would have been greater. So by looking now and seeing processes like this, we think we can understand what happened 4 billion years ago.
Well, Bruce, where will your team actually be when they first see some of this science coming in?
We have a distributed science team, and some of the members will be at the University of Colorado, where I'm stationed, at University of California, Berkeley, at Goddard Space Flight Center, and at several other institutions around the country and a couple abroad as well.
And you expect to start seeing some of that science when for the first time?
We go into orbit in late September of next year. It takes us about 5 weeks to commission the spacecraft to get ready to do the observations, and then we'll start to get the measurements. I'm thinking that it will take us about 3 months to be sure we understand how the instruments are working, make sure they're calibrated properly, and we can begin to understand what the data are telling us. So I think we're looking at beginning to have some of our key science results starting early in 2015, about 14 months from now.
Yeah. Well, Bruce, thank you very much, and sure your team has with so much effort over the years to put this mission together. This is coming to a pinnacle and apex here in just less than an hour.
This is incredibly exciting, and you're sitting here with the same view that I've got of the rocket on the pad up on the screen here, and we're just excited right now and hoping for the best.
Bruce, thanks very much.
Thank you.
And we're at T-minus 46 minutes, 7 seconds and counting. This is Atlas Launch Control.
LH2 70%. Roger. LH2 at 80%. Roger.
T-minus 43 minutes.
Atlas LO2 at 90%.
Roger. LH2 at 90%. Roger.
T-minus 42 minutes.
ECB at flight pressure. Roger.
LC, RCN1.
Go ahead.
Roger that. L was reporting that we are now green on all weather constraints. Range is green.
Roger.
T-minus 40 minutes.
Start final open loop FTS test. Roger.
Step 570, Atlas LO2 at 97.5%, topping started.
Roger. All steps are complete through step number 590. Step 620, Centaur LH2 at 96.2%, topping started. Roger. Perform Centaur LH2 fill and drain valve cycle test. Roger. Perform Centaur LO2 fill and drain valve cycle test. Roger.
Centaur LO2 fill and drain valve cycle test is complete.
Roger.
Step 630 Centaur LH2 fill and drain valve cycle test complete.
Roger. Perform Centaur SRV and LH2 SVV cycling test.
Roger.
This is Atlas Launch Control, T-minus 35 minutes, 25 seconds, and counting. As we've heard, we've completed the cycling of our fill and drain valves on the Atlas and Centaur, and we are continuing without any issues on the vehicle whatsoever. We have some additional tests coming up. We've got a fill and drain valve test on the Atlas test right now, and a functional test. See the Coast Guard offshore there patrolling the waterways and security, NASA security. Right now, the only thing going on is our launch weather officer, Clay Flynn, reports that some of the field which measure the electrical potential in the area are beginning to toggle back and forth between the acceptable limits and are being watched with some indication that there is a cirrus anvil cloud overhead that makes those field mills at time go out of specification. But right now all the field mills are green. But that's something that may happen as we have some clouds begin to move into the area. The field mills that measure electrical potential could go in and out of limits. So at the moment we had one go out, now it's back in, and at the moment we're green. But that could continue to happen about any time through the balance of the count and into the launch window, as long as we have some cloudiness approaching us from the northwest. Otherwise, we're continuing with our fill and drain valve cycling. We've completed the first round of that and going into concluding that activity, which will keep it completely on schedule for a 1:28 p.m. liftoff. At T-minus 33 minutes, 16 seconds and counting, this is Atlas Launch Control.
Are complete. Roger. Resume Centaur LH2 topping to flight level.
Roger.
Resume Centaur LO2 topping to flight level.
Roger.
LC Redline Monitor.
Go ahead, Redline Monitor.
Yes, LC at T-minus 43:15 approximately. Redline Monitor indicated an OTC on measurement Charlie Uniform Kilo 020 Echo. That is a Centaur liquid oxygen delta pressure measurement.
Roger. Centaur Pneumatics, LC.
Centaur Pneumatics.
Roger. You observing any problems with tank pressures? Or did we maybe pick something up during the vent valve test?
I don't see anything out of the ordinary. The Centaur vent valve cycle test seemed to be nominal. What was the measurement again?
Charlie Uniform Kilo 020 Echo. Okay. Tank pressures at this time are indicating nominally.
Tank pressures at this time are indicating nominally, correct.
Roger. AC, LC, channel 1.
ACN 1.
Roger. Redline Monitor reported a OTC violation on Charlie Uniform Kilo 020 Echo. Centaur LH2 Delta P measurement. Please convene the anomaly team and provide a recommendation.
Roger.
T-minus 31 minutes.
LC is redline monitor.
Go ahead.
Yeah, we've been reading in band on that measurement Charlie Uniform Kilo 020 Echo for some time now. Can we go ahead and reset that violation, acknowledge that?
Roger, reset it at this time.
Roger, in work.
This is Atlas Launch Control, T-minus 25 minutes, 45 seconds and counting. Today's launch is dedicated in memory of Grover Hall and Adam Crocker. In his 39-year career, Adam Hall with Lockheed Martin Space Systems and also Adam Crocker held a number of key engineering management positions, including a vice president of NASA Systems, overseeing Magellan, tethered satellite, and flight telebotics resurfacer. Adam Crocker was a student at Colorado State University, an Air Force ROTC cadet, a pilot, and a young man interested in space. His father, sister, and brother-in-law are members of the spaceflight community at Lockheed Martin and United Launch Alliance, who have all been involved with the MAVEN mission and the Atlas program. So again, our dedication of this launch to Grover Hall and Adam Crocker.
LC, step 810, FTS open loop test is complete.
Roger.
LC, ALO.
Go ahead.
Step 640, Atlas LO2, fill and drain valve cycle test complete.
Roger.
Atlas airborne vent valve functional test is complete.
Roger. Perform pogo suppressor charge.
Roger.
This is Atlas Launch Control, T-minus 21 minutes, 33 seconds and counting. The Atlas V rocket has two stages. The Atlas booster stage is 106.5 feet long, 12.5 feet in diameter, and it burns two propellants, RP1, which is a highly refined kerosene. There's approximately 26,000 gallons on board, and liquid oxygen. There is approximately 50,000 gallons loaded on board the Atlas. The Centaur stage is 41.5 feet long, 10 feet in diameter, and it burns liquid hydrogen and liquid oxygen through its RL-10 engines. There's approximately 12,000 gallons of hydrogen loaded aboard now, the Centaur stage, and 4,000 gallons of liquid oxygen. The height of the vehicle on the pad is 191 feet. And it will weigh approximately 750,000 pounds at liftoff. Right now we're not working any issues. The field mills currently are green, and they may drift in and out occasionally with the encroachment of some cloudiness from the northwest. And the one other indication that we were working was associated with our fill and drain valves is apparently a transducer issue and does not appear to be a concern. So we're at T-minus 19 minutes, 33 seconds and counting. This is Atlas Launch Control.
LC, ALO.
Go ahead.
Step 690, pogo suppressor charge complete.
Roger.
T-minus 19 minutes. LC Flight Control Channel 1.
Go ahead, Flight Control.
Step 750 BRC SIB 1 and SIB 2 voltage checks are complete.
Roger, LD. NLM, Channel 1.
NLM's on.
Roger.
LC, AC on 1.
Go ahead.
Roger, sir. I'm ready to provide the outbrief for the redline monitor issue.
Proceed.
Roger, sir. The team has data associated with measurement Charlie Uniform Kilo 020 Echo, and the transducer is indeed reading a little high to family, but it's within spec. There is no concern with proceeding through the rest of the count and flight. We should not see a recurrence of this issue with any planned operations. Recommendation is to proceed.
Roger. Copy and concur. NLM.
NLM copies and concurs.
And LD.
LD concurs.
RD 180 transducer converter calibration is complete.
Roger. RC, conduct weather briefing on Channel 8 Weather Conference Net.
Roger. LWO, range coordinator, Channel 8.
LWO.
Please stand by for final weather brief.
Standing by.
Following personnel acknowledge standing by for the weather brief. NLM.
NLM.
LD.
LD.
AFLD.
AFLD.
LWO, please proceed with your brief.
Yes, sir. This is LWO for the L-30 weather brief on Weather Brief CC Local and Channel 8. You should have a satellite picture of the peninsula of Florida on your CCTV monitor at this time. You'll know the blue quarter there is the amble cloud tool. We continue to have amble cloud streaming over the pad. It is below criteria, so we are go and don't view that as a low threat of violating any amble cloud criteria during the beginning of the window, more so towards mid to latter part of the window. Likewise, there are cumulus clouds in the vicinity. Let me go ahead to the radar. There are some cumulus clouds embedded in that anomalous propagation that you see, those light blues that you see over the Cape and south of the Cape. However, the peak, we have the one in the area, the tops of all those clouds are topping out at about 8,000 feet. It would only be a fly-through constraint if it was up to about 12,700 feet. So it looks like at this time, although they should continue to build at this time, there's not a threat for we're not violating cumulus cloud rule violation. However, the more heat we get and the closer the front gets here, we'll have a greater threat during the mid to latter part of the window. Still a potential, but at this time all LCCs are go and expected to remain go during the beginning of the window. Taking a look at the the winds out of complex 41. Winds still relatively light, gusting to about 7 knots. They shouldn't gain much more. I'm going to pin gust 15, which perhaps is a little bit high. In terms of the direction, they're still out of the northeast. I think eventually they'll become southeast, but nevertheless out of the east and staying under 15 knots for peak gust. In terms of the temperature at the present time, we're in the about 78 degrees, and we'll bounce around 78 to 80 on that order. In terms of the upper level profile, the winds did drop off a good little bit between 20 and 25,000 feet. Looks like almost 20 knots in this range. Don't expect to see a great change in drop off of the profile for the balance of the count window. In terms of the ops forecast, looking for multiple cloud layers, 7 miles of visibility, winds from the east, out of the easterly direction, 10 gusting to 15. We should see isolated showers during the window, but the front end of the window certainly looks better. Temperature in the 79 to 82 range with a 40% chance of violation. All LCCs are go at this time. There's no change in the 24-hour, no change in the 48-hour. In terms of proton flux, it remains in normal background levels. And in terms of the exposure, low threat of any type of lightning, not expecting any type of lightning in the next hour to two, and then a small threat after 2 o'clock with the greatest threat after 1400 or 1600 local. This concludes the weather brief. Pending your questions, sir.
Range coordinators, no questions.
Hello, LD here. One question. What time of the count do you stop latest you'd call a field mill by?
I'm sorry, sir. I couldn't hear your question.
When is the last point you would call a field mill violation per our CONOP?
Sir, the last time we'll get a field mill update is 1 minute out from T0. They update a few seconds after the top of the hour, so it would be probably 50 seconds. 50 seconds, at not later than 50 seconds after 1 minute prior to T0.
Roger that. Thank you.
Yes, sir.
FLD, no questions.
NLM, no questions.
This is Atlas Launch Control, T-minus 13 minutes, 16 seconds and counting. We have a hold coming up at T-minus 4 minutes. That is a 10-minute hold. And as you heard, the weather briefing right now, the weather is go, and our one technical issue has been cleared. So we're continuing to press on to a launch at 1:28 p.m. At T-minus 12 minutes, 50 seconds and counting. This is Atlas Launch Control.
LCFC Channel 1.
Go ahead.
STEP 800, the primary address text hex file, address _ alpha victor 38 _ 05 with SDL-CRC of 0 Echo 1 Bravo has been received, verified, and is ready to load into the FTINU.
Proceed with load.
Copy.
T-minus 11 minutes. T-minus 10 minutes.
This is Atlas Launch Control, T-minus 9 minutes and counting. Headed down to hold at T-minus 4 minutes, which is 10 minutes in duration. At this time, the launch vehicle is green, the range is green, and the MAVEN spacecraft is green. MAVEN launch will weigh 5,421 pounds. It has 2,000 solar cells on its 4 solar array panels. They generate between 1,150 watts and 1,700 watts, depending on the spacecraft's location above Mars. Once we get into our final hold at T-minus 4 minutes, we'll have the final polls from Omar Baez and the NASA launch team, and then the polling of the United Launch Alliance launch team. But at this time, we continue to press toward a launch at 1:28 p.m. This is Atlas Launch Control, T-minus 7 minutes, 50 seconds, and counting.
Step 830, primary address tech hex file, address underscore alpha vector 038 underscore 05 with SDLCRC 0 Echo 1 Bravo has been loaded into the FTINU and verified.
Roger. All steps are complete through step number 850.
T-minus 6 minutes.
Fuel fill sequence is complete.
Roger.
This is Atlas Launch Control, T-minus 5 minutes 15 seconds and counting. Once we lift off from the pad, the Air Force tracking stations here at the Cape will be supplying the data, and supplemented by the South Florida data from Jupiter Inlet at about a minute 14 into the count.
Roger.
Then the Antigua station will provide coverage until acquisition through Tidris East, about 13 minutes into the flight. Standing by to go into the planned built-in hold at 4 minutes. Going into the hold in 5, 4, 3, 2, 1. T-minus 4 minutes.
T-minus 4
and
minutes
holding.
holding. This is a program 10-minute hold.
Verify the FCO, RCO, and OSM hold fire switches are in the proceed position.
Ready to proceed.
TTP status verified.
Roger.
This is the NLM on the NLM net with a final launch readiness poll to release the hold at T-minus 4 minutes. NASA CE.
NASA CE, go.
SMA.
SMA is go.
SMD.
SMD is go for final count.
NASA Mission Manager.
Mission management is go, Omar.
NAM.
NAM is ready.
Copy that. The NASA team is ready for launch.
Perform launch on time verification.
Roger.
Now we're going to astronaut Michael Hall aboard the International Space Station, launched on the ISS on September 25th, 2013.
Greetings from the International Space Station. I'm NASA Flight Engineer Mike Hopkins of the Expedition 38 crew. We want to wish the MAVEN team a successful flight to Mars. Like a lot of the research we're conducting on the International Space Station, understanding the red planet's atmosphere is essential to NASA's goal of safely sending humans there one day. From the International Space Station, best wishes for a fabulous mission.
And with best wishes from astronaut Michael Hopkins, we'll be standing by to come out of the planned built-in hold, not working any issues in the countdown. We'll have our launch conductor Doug LeBeau from United Launch Alliance polling his launch team.
LC flight control on 1.
Go ahead.
Launch on time verified.
Roger. Verify solar radiation acceptable for launch.
Verified.
Spacecraft to internal power.
Roger.
LC switch to ready position. All steps are complete prior to the status check.
Once we have liftoff, we'll be hearing United Launch Alliance Atlas V telemetry manager Rob Gannon providing the flight ascent calls for the Atlas as it moves into space. We'll get the final go for Atlas readiness and Centaur readiness at T-minus 25 seconds.
Status check to proceed with terminal count. Atlas systems, propulsion.
Go.
Hydraulics.
Go.
Pneumatics.
Go.
LO2.
Go.
Water.
Go.
Centaur systems, propulsion.
Go.
Pneumatics.
Go.
LO2.
Go.
LH2.
Go.
Has gas.
Go.
Electrical systems, airborne.
Go.
Ground.
Go.
Facility.
Go.
RFFTS.
Go.
Flight control.
Go.
Instrumentation.
Go.
COM.
Go.
Timer.
Go.
GCQ.
Go.
Umbilicals.
Go.
ECS.
Go.
Redline monitor.
Go.
Quality.
Go.
Op safety manager.
Go.
ULA safety officer.
Go.
Vehicle system engineer.
Go.
Range coordinator.
Clear to proceed.
Launch director.
Launch vehicles ready to launch.
Proceeding with the count. T0 is planned for 18:28 Zulu. Set count to start at 18:24 Zulu.
Roger. T0 is set for 18:28 Zulu. Count will start at 18:4 Zulu.
And we've just had a go for launch from MAVEN spacecraft mission director and project manager David Mitchell. Once we're at T-minus 1 minute 55 seconds, the automatic sequencer will take over the automated control of the countdown from that point to liftoff. The RD-180 engines will ignite about 3.8 seconds before liftoff.
Spacecraft on internal power.
Roger. All steps are complete prior to terminal count.
Picking up the count in 30 seconds.
On my mark, time will be T-minus 4 minutes and counting. 3, 2, 1, mark. T-minus 4 minutes and counting.
3:55.
Ground pyros enabled.
T-minus 3.5 minutes.
Three minutes.
Securing LO2 topping.
Atlas tanks to flight pressure.
250.
FTS internal.
T-minus 2 minutes 30 seconds.
Two minutes.
Vehicle power internal.
Launch sequencer start.
150.
Securing Centaur LH2.
Securing Centaur LO2.
140.
Launch enabled.
FTS armed.
T-minus 90 seconds.
$120.
Orca's armed.
FCS count started.
$110.
Vent valves locked.
One minute.
Rock, report range status.
Range green.
Standing by for final Atlas and Centaur go.
40. Stable at step 3.
Status check.
Go Atlas. Go Centaur.
Go Maven.
20. 15.
T minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Main engine start, ignition, and liftoff of the Atlas V with MAVEN, looking for clues about the evolution of Mars through its atmosphere.
Control. Mark. Everything looking good. Still at 100% rated thrust on the RD-180. Vehicle rates are looking good. We do have roll program in, right as expected. We are actively controlling the mixture ratio. Valve position looks good. Thrust regulator valve position looks good. Speeds are good. And vehicle's operating as expected. Continue down the center of the range track. Everything is looking good. We're now 1.6 nautical miles of altitude, 1.1 miles downrange, traveling at a little over 1,000 miles per hour. And we have ended our roll programs. Everything is looking good, continuing at 100% thrust. We are now passing through the sound barrier. MAVEN is now supersonic. RD-180 continues to operate at 100% rated thrust. We are about to pass through max Q. And vehicles passing through max Q. Rates look good. Engine continues to operate at 100%. And we have throttled down to 95% thrust, right on time. We're now 10 nautical miles in altitude, 7.4 miles downrange, traveling at 2,200 miles per hour. And everything is looking good. Continue to operate at 95% thrust. Coming up on our next mark event, I expect to enable Q alpha steering. And steering's enabled. Body rates look as expected for bringing and steering. Vehicle is now 50% of its liftoff weight. And we're about to fire the pyro valves to activate the second stage reaction control system. Pyro valves have fired. System has pressurized. And the RD-180 continues to operate as expected at 100% rated thrust, or 95% rated thrust correction. Rates are looking good. Continue to accelerate, passing through 3 Gs. PU control looks good. And continue to fly right down the center of the range track. We are now 35 miles in altitude, 70 miles downrange at 6,000 miles per hour. Reaction control system is now fully pressurized. And continuing to operate at 95%. Good PU control. Smooth body rates. Continue to have nominal acceleration. Vehicle is now 25% of its liftoff weight. We are now throttling the engine to actively control at 5 Gs. We have started boost phase chill down. Housing temps are reacting as expected. Continuing to operate the RD-180 as expected. We are now flying a 4.6 G throttle profile. Engine is throttling, getting ready for booster engine cutoff. We have BECO coming up on staging. We have stage separation. Everything is looking good. We have pre-start on fuel and locks. Everything's looking at ignition, full thrust. Centaur main engine is up at 100% rated thrust, coming up on fairing separation. We have fairing set. And rates look good for fairing separation. Should be cutting back in on closed loop control. And we've done purge firings in the reaction control system as expected. We do have closed loop control reestablished after fairing jettison. The RL-10 continues to operate as expected, nice and smooth. PU is in open loop control as expected. Axial acceleration is steady. We are now 93 or 107 miles in altitude, 426 miles downrange, traveling at 11,700 miles per hour. Vehicle is continuing right down the center of the range track. Everything looking good. We are seeing our expected thruster, reaction control thruster, thermal maintenance firings. Body rates are nice and smooth. Everything is continuing to look good. Engine operating parameters are good. We are now in the process of executing a 9-minute, 30-second first burn of Centaur. Everything is looking good. We have closed loop control on the PU system a little over 20 seconds ago. That transition looks as expected. Continuing to operate at a LOX-rich mixture ratio. We have now begun our roll to TDRS attitude. Our delta PE for boost phase or preliminary look gives us 78 pounds of delta PE. That's 1 sigma high to our nominal rate. We had format change. And continuing to get clean data. Engines continue to operate as expected. Then we see our expected activity on the reaction control thrusters. 152 miles in altitude, 826 miles downrange, traveling at 12,500 miles per hour. And PU continues to operate on the lock stop. That's as expected for this time in flight. We're seeing some noise in telemetry at this time, but enough data is coming through. We're seeing steady operating pressure levels on the RL-10. Everything is looking good. And I continue to see the mass error signal correct itself as expected. Engine pressures are nice and smooth. Accelerating smoothly, a little over half a G at this time. And we're seeing all of our reaction control system temperatures come together as we condition the system. Everything looking good. And PU's continuing lock stop. Everything looking good. Here we see our expected thruster firings. Very little roll control has been needed. Passing through 9 minutes into the mission, everything looking good. RL-10 is operating nominally. Seeing smooth body rates.
Have loss of contact here at the Cape in communications. Antigua is now providing data.
Engine operating normally. Everything looking good. Steady acceleration at 0.56 Gs, right down the center of the range track. 168 miles in altitude, 1,400 miles downrange, traveling at 14,000 miles per hour. Everything is looking good. Operating parameters on the engine, very steady, nice and smooth. We are seeing oxidizer error in the PU system control coming towards nominal. The valve has come off the stop. Seeing active control of the PU valve now on the RL-10. Vehicle continues to burn normally. And since we have launched at the beginning of the window, we are expecting our spacecraft separation time right at 52 minutes, 42 seconds into the mission. And continuing to see active control, Centaur PU. Engine pressures are reacting as expected to the change in mixture ratio. Smooth body rates. Nominal performance down the range track. We are inside of 3 minutes to MECO 1. PU controls coming up near the nominal mixture ratio. Engine continues to operate as expected, seeing the normal small adjustments in engine pressures as the PU valve slews. Our PU metal. Rates are good. Pressures are good. RCS activity is right as expected. Very little roll control is being required out of the reaction control system. Engine is burning normally. We are now inside of 2 minutes to MECO 1. MAVEN is continuing to fly normally. Once we complete this burn of Centaur, first burn of Centaur, we will enter a 27-minute, 36-second coast phase, followed by a second burn and then spacecraft separation. Continuing to look at very good telemetry data. Engine is good, rates are good. As noted before, seeing normal activity in the control system with very little roll control needed. PU is now operating near nominal mixture ratio. And everything is looking normal on the vehicle. And we're approaching 30 seconds to MECO 1. Coming up on MECO 1, vehicle's looking good. 10 seconds to a expected MECO 1 time. Open loop on PU, locked, and MECO. We have cutoff. Cutoff time right as expected. Everything looks good. 4S settling thrusters are on. And we are beginning to reorient to our PTC attitude and starting our PTC roll. And we are actively controlling pressure in the tank by controlling our vent valve locking. Everything looks good there. Now climbing into our PTC roll rate of 1.5 degrees per second, and we have now achieved that rate. Continuing to see settling as expected.
And our nominal orbit right now during the coast phase is 87 nautical miles by 170 nautical miles. Coming up, losing our data through Antigua and acquisition through the TDRS East tracking and data relay satellite.
Good bus voltages. Plenty of pressure in our Centaur helium bottle. Continuing to see our PTC roll. Very clean data. We're seeing minor dropouts as the vehicle's rolling as expected. But we recover and continue to see good data.
While we're in the coast phase, we're going to be looking at some launch replays from the ground.
And we have had a vent valve cycle. Center hydrogen tank. Pressure's dropped as expected. Bus battery voltages look good. Helium storage looks good. Vehicle's going to roll and reorient itself as expected. Very clean, active autopilot control. Can we see our expected reaction control system activity? And continuing with 4S settling. Next event we'll see is starting to ramp our settling down to a 12.5% duty cycle. It'll kick in approximately a little over 30 seconds from now. Currently have a telemetry dropout, and we've recovered telemetry. Didn't see normal coast phase performance. And we've begun our ramping of Centaur settling down to a 12.5% duty cycle. Bus battery voltage is good. Helium storage looks good. Next event we're looking for is securing our C-band transponder. And we have secured the transponder within a couple seconds of nominal. And we've in the process of executing a PTC roll reversal. And we're now steadying out. telemetry dropout in progress now. Nothing unexpected for this time of flight. And we can see with the recovery of data that we have achieved our roll reversal. Now settled out at a minus 1.5 degree per second roll rate. And next mark for approximately 6 minutes from now is our next mark event we are looking for is our duct flush on Centaur. It's just around 5 minutes from now. Vehicle continuing in normal coast phase. Pitch and yaw rates are steady, right around 0 degrees per second as expected, and we're at the minus 1.5 degree per second roll rate. Bus battery voltages are good. Tank pressures, helium storage pressures looking good. And reaction control system activities as expected this time in flight. And we're in the middle portion of our 27.5-minute coast phase. Continue to look good. Centaur pressures and voltages are looking good. Rates are smooth, right as expected. As noted before, we will be executing a second burn of Centaur. Duration of that is 5.5 minutes. Following that, we will have a 5-minute, 49-second coast phase to a spacecraft separation, 52 minutes, 42 seconds mission elapsed time. Centaur and MAVEN continue to coast nominally. Coming up on 1500 seconds. Mission elapsed time. Bus battery voltages look good. Reaction control system firings look good. Body rates look good. Everything looks normal. We're now 1 minute to our duct flush expected time. Vehicle parameters are normal. "30 seconds to the duct flush. And we're executing our duct flush. Everything looks good. Inlet pressure shows we have closed the valve. Sequence timing was as expected. Continue to see expected performance, good bus battery voltages, good tank and helium storage bottle pressures. Rates are smooth. Passing through 1650 seconds into the flight. And everything looks good. PTC roll continuing to be executed at -1.5 degrees per second. Settling duty cycle at 12.5%. Bus battery voltages are as expected, a little over 30 volts DC. Storage bottle pressures are good. And tank pressures are good. And we're now executing a roll reversal for our PTC. We are seeing the rates change. Coming through 0%, heading towards a positive 1.5 degree per second roll. Passing through 1.3 degrees per second, approaching our target. And we're settling out at a positive 1.5 degree per second PTC roll. And passing through 1,800 seconds into the mission, everything is looking good. Weights are steady with the pitch and yaw at 0 as expected, and a positive 1.5 degree per second roll rate. Everything else is stable. We have no change for bus battery voltages, are right as expected. Same conclusion with storage bottle pressures for a helium system. And tank pressures look good as well. Passing through 1,900 seconds into the mission, everything continues to look good. No change from previous reports. All parameters are monitoring right as expected. Nice and smooth. And we just passed through 33 minutes into the mission. Everything is continuing to look good. And we're now seeing some active propellant conditioning in the central LH2 tank. Vent valve cycles are bringing tank pressure down. And we're now at a 50% duty cycle on RCS settling. Fuel tank pressure steadied out right as expected. As before, bus battery voltages continue to look good. Tank pressures look good. And we're now in the process of turning to our MES-2 attitude. Vehicle sequence continues to be executed nominally. Seeing some changes in pitch and yaw rates as the vehicle reorients itself. Roll rate continues at our PTC roll rate. Just passed through 36 minutes in the mission. Everything continues to look good. And now 5 minutes to MES-2. Passing through 37 minutes into the mission, the vehicle continues to change its pointing for MES-2 attitude with a positive 1.5 degree per second PTC roll. 50% settling is in progress as expected. We're actively controlling fuel tank pressures, conditioning the propellants. Thirty-eight minutes into the mission, everything looking good. And we are despinning our PTC roll as expected. We are now inside of 3 minutes to second burn. Our second burn sequence will begin with switching to 100% settling. We will then increase propellant tank pressures, followed by LH2 pre-start, 33 seconds prior to MES. In an LO2 pre-start sequence, it starts just under 18 seconds before MES. Two minutes to second burn. Vehicle continues to reorient itself to our second burn attitude. And we're about to start our pre-MES sequence. And we've begun our pre-mess sequence. We're at 100% settling. And we're now adjusting tank pressures, fuel tank pressure coming up. Everything's looking good for the second burn of Centaur. This will be a 5.5 minute nominal burn. Now 20 seconds to pre-start on LH2. Continuing to change our tank pressures as expected. And we have LH2 pre-start. PU valve is moving to a start position. Locks pre-start. Looking good, coming up on mass. Ignition, full thrust. Main engine is up to nominal operating parameters. Everything looks good. And we're seeing expected start transient is being nulled out in rates. Engine operating pressures are looking good. We are now in closed loop control on PU. We're correcting out a bit of a LOX bias. And coming back up to a nominal mixture ratio. Seeing expected settling, we are executing a hydrazine burn-off sequence during the second burn to maximize vehicle performance. Engine pressures are looking good, rates are good. PU is controlling normally. And we're continuing to see expected reaction control system activity. Engine pressures are good, nice and smooth. PU control is very smooth. Just a little off nominal mixture ratio. Vehicle rates are nice and smooth. Everything looks good. And we're inside of 200 seconds to MECO 2. PU is now controlling nominal mixture ratio point. And engine pressures have been reacting to our changes in mixture ratio as expected. Engine operation is nice and smooth, good pressures. Vehicle rates are smooth. Mass air is smoothing out very nicely. Continuing to see expected reaction control system activity. Virtually no roll control appears to be needed. PU is continuing to control nominally. Now making a slight LOX correction. Engine pressures look good. Centaur continues to burn normally. Good engine pressures, good body rates. RCS activity is right as expected. We are smoothly accelerating. 1.26 Gs. Good PU control. .100 seconds to MECO 2. Everything looking good, burning normally. Rate smooth, PU smooth, engine pressures steady at the appropriate levels. Inside of 1 minute to MECO 2. Following MECO 2, we'll have a 5-minute, 49-second coast duration to a spacecraft separation at 52 minutes, 42 seconds from liftoff. Everything looks good, 30 seconds to cut off. Inside of 20 seconds. Ten seconds to nominal cutoff time. Coming up on second main engine cutoff. And we have cutoff. Approximately 4 seconds long, well within our dispersions. Everything looks good. We are 4S settling. And vehicle rates are nulling out from the shutdown transient. Everything looks good. We are now executing our pre-spacecraft separation sequence. Everything looks good there. We are reorienting to our SEP attitude.
As mentioned, it'll be almost 6 minutes before spacecraft separation occurs.
Rates look good. Continuing to change our planning for spacecraft SEP. For this mission, there is no spin-up required. All rates will be nulled for separation. We're now at a 50% duty cycle on reaction control system. We've unlocked the vent valve out on time. Venting the hydrogen tank. Pressure's coming down as expected. And everything looks good in this pre-spacecraft SEP sequence. Body rates are nulling out. Tank pressures look good, right where they're supposed to be. RCS activity is good. Continuing our expected sequence.
We're now 49 minutes, 10 seconds into the flight of the Atlas V with MAVEN. Spacecraft separation is at 52 minutes, 42 seconds.
Yeah, 3 minutes to spacecraft SEP. Everything looking good in this coast phase coming up to spacecraft set. Vehicle sequencing continues to be as expected. Two minutes to spacecraft up. Everything looking good. Yeah, we're seeing our expected performance from the reaction control system. Body rates are now leveled at 0. We've apparently achieved our pointing for spacecraft set. One minute to spacecraft separation. "30 seconds to spacecraft up. Everything looking good." "10 seconds to spacecraft set. Everything looks good. Bait's nulled out. We have spacecraft separation. Both brake wires indicate MAVEN has successfully separated from Centaur. Everything looking as expected. We are reorienting to CCAM. And with the successful separation of the MAVEN spacecraft, this concludes the commentary for the launch of AV-38 with the MAVEN spacecraft.
And we're now 53 minutes, 18 seconds into the flight of MAVEN. MAVEN is now cruising on its own. We will be having our NASA Launch Director, Omar Baez, come over very shortly and talk to us about how the countdown and how the flight of the Atlas V went. The spacecraft, over the next hour or so, we'll be going through a number of activities, including deploying the solar arrays and going power positive with the sun. And we will have a spacecraft status at our post-launch news conference scheduled for 4 p.m. So at this point, all of the data indicates that we've had a very good flight of the Atlas. We'll have Omar Baez come over and talk to us about that here in just a moment. And MAVEN is now on the way to Mars. So we'll be standing by now. They are watching carefully data that will be coming in through the Canberra tracking station. And the Perth tracking station in Australia is also actually the station that makes the initial acquisition of MAVEN before it passes over Canberra. This is Atlas Launch Control, 56 minutes, 12 seconds into the flight of the Atlas V with MAVEN. Spacecraft separation has occurred, and so now joining us here at the Console and Mission Director Center is Omar Baez, who was our NASA Launch Director and NASA Launch Manager for the countdown and launch today. So, Omar, first of all, tell us how the flight of the Atlas appeared to go.
Thank you, George. The flight of the Atlas and Centaur were flawless from everything we could tell. Separation occurred on time. All the marked events occurred on time. We got it off on the first opportunity, and the separation looked fine. So all we're waiting for now is for the spacecraft to go through their sequence and deploy their solar arrays. And that should happen anytime in the next 5 to 15, 20 minutes or so.
How did the countdown go from your perspective?
We had a nice, quiet countdown. Major things we were worrying were electrification in the air, and there was a bunch of anvil clouds that were streaming over the area and had the potential for triggering lightning if we were to launch during those events, but that it was short-lived. We had 2 or 3 little scares there, and then we pressed on. It started to get cloudy in the area here, but none of that weather really violated any of the constraints. So we were good from a weather perspective. We worked a minor pressure transducer issue, and it just turned to be a little bit out of family high, but within the tolerance. So there was no vehicle issues to speak of.
So if MAVEN phones home, then we've had a very successful launch. Tell us what's coming next. It's not far to our next Atlas launch after this one here at Kennedy.
Yeah, the next Atlas launch will be in January, the TDRS L mission, but the ULA team does have one before that out at Vandenberg on December 5. And so we're looking forward and wishing them luck on that so that they can come back and work on TDRS for us.
Well, Omar, thank you very much. It's all good news on the flight of the Atlas V. Thank you very much. And we're now 58 minutes, 48 seconds into the flight of MAVEN. This is Atlas Launch Control.
Com check, channel 1.
Copy, com.
Go ahead, Ed.
Hello there, team. This is Charlie Bolden. I just wanted to take a moment to thank everybody. All day we've been saying, go Atlas, go Centaur, go MAVEN, and that's for a reason. It's because this is the effort or the effort of a really tight team that's been working pretty hard. The one thing I will tell you is that I would hope that this mission will be a model for the ones that come after it. They say imitation is the grandest form of flattery. And I think the best way that we can pay tribute to all of you is to have other missions come in cost and on schedule the way that you all have done, because that's what's going to make people have faith in us and believe what we say when we talk about doing even grander things like putting humans on Mars. But again, you all have done an absolutely incredible job. Let me thank everybody, and I'll let you go back to work so you can finally get home family, hopefully. But thanks again for everything. Great job.
Our NASA Administrator, Charlie Bolden, has just congratulated the Atlas V launch team, including United Launch Alliance and the NASA Launch Services Program. We have had confirmation that the solar arrays on MAVEN have deployed. We got that confirmation at 2:54, and the arrays are out. We are now waiting for a look at the data of the overall state of health of the spacecraft, and that will take a little bit of time to come in, and the spacecraft has just begun reorienting itself into the phone home attitude, and they will be looking at the data there over the next half hour, and we should be able to have our post-launch news conference at 4 o'clock, assuming they get all the data that they're looking for, indicating that the spacecraft state of health is good. But we do have confirmation that the solar arrays did begin to deploy on time, and that is complete, and they are out. So at any rate, they are now verifying that the spacecraft is power positive and looking at the overall state of health of MAVEN. But everything indicates that everything has gone completely nominally. So at this point, this will conclude our launch coverage on NASA television of the launch of MAVEN on the Atlas V. Our next event will be the post-launch news conference at approximately 4 p.m. This is Atlas Launch Control. Hello everyone, this is our mission science briefing for MAVEN. Still on schedule for a launch at 1:28 p.m. on Monday. we'd like to start with a brief status of what is going on with MAVEN and the Atlas V at the launch pad, and things are relatively quiet. This is a crew rest day for the launch team. Everything is in readiness at the pad. The only activity going on is battery charging of the MAVEN spacecraft and monitoring of the state of health. And our weather forecast for Monday has remained the same, a 40% chance of no-go, primarily due to cloud constraints, and then 60% no-go on Tuesday and on Wednesday because the wind will increase some on Tuesday and Wednesday. So Monday remains our most favorable day, 40% no-go or 60% go. And at this time, all is in readiness to pick up the countdown at 6:28 a.m. on Monday morning. We'll start now with our presentations. First, Michael Meyer, the lead Mars scientist from NASA headquarters in Washington. Bruce Jakosky, the MAVEN principal investigator from the Laboratory for Atmospheric and Space Physics at the University of Colorado at Boulder. Janet Luman, the MAVEN deputy principal investigator from the University of California at Berkeley. Nick Schiller, the MAVEN IUVS instrument lead from the Laboratory for Atmospheric and Space Physics at the University of Colorado at Boulder. Paul Mahaffey, the MAVEN NGIMS instrument lead from NASA's Goddard Space Flight Center in Greenbelt, Maryland. And David Mitchell, the MAVEN SWIA instrument lead from the University of California at Berkeley. And we'll begin first with Michael Meyer. Michael.
Well, thank you, George. For millennia, Mars has been a source of myth and fable. And it's only a little over 50 years ago that we first sent a planetary probe into space to move from just myth and fable to actually observation and measurements. If I could have the first graphic, please. Our sister planet Mars has been the focus of planetary exploration primarily because it's a key to understanding the origin and evolution of our planets. And so we've, over a little over a decade, we've had spacecraft, orbiters, and landers that have worked synergistically to help unveil what is happening on Mars and what may have happened in its past. And as we see MAVEN, here we are getting ready to launch, and is going to answer a key question about Mars evolution. And with that lead into, as we can see, other spacecraft that are either international, as in provided by ESA or by NASA, going into a future of very robust Mars exploration and trying to not only tell us about the evolution of climate and geology, but also of life. So with the next graphic, I'd like to say, you know, while we've been doing all this, what have we learned? Well, one of the things that has been unveiled is that looking at Mars and looking in the near subsurface, we see that Mars has actually quite an inventory of ice, water ice, in its polar areas. And we look more at the geology and mineralogy of the planet, we can see that water once flowed on the surface of Mars. At least that's what it looks like. But with rovers going to the surface and landers going to the surface, we see mineral evidence of water having been at the surface of Mars. We see hematite and we see gypsum discovered by the Mars exploration rovers. And just recently, with the rover Curiosity, we found a rock called a conglomerate. This is the type of rock that we only find on Earth in dried riverbeds. So we now have evidence with other measurements showing that there is water flowing on the surface of Mars. We know that it was the environment at one point in time on Mars was able to support microbial life. But you look at the Mars today, it's cold, it's dry. We want to know what happened. And with that, I'll turn it over to George to lead the rest of the conference.
Thank you, Michael. And now to Bruce Jakosky. He is the MAVEN principal investigator from the Laboratory of Atmospheric and Space Physics at the University of Colorado at Boulder. Bruce?
Thank you, George. Michael talked about the geological evidence that there was water on ancient Mars and the mineralogical evidence. Something clearly happened. Water was abundant on early Mars, the environment was something that was capable of supporting liquid water, yet today we see a cold, dry planet that is not able to support water. What we want to do is to understand what are the reasons for that change in the climate. In order to, in looking at the drivers of the change in climate, we're going to be able to understand the history of the geology of the planet and the history of the potential for life, the history of the habitability of the planet, because both of these depend pretty much on the history of water, the history of the environment, the climate on the planet. With Mars having had liquid water early on, we think that there must have been a thicker atmosphere that would have produced greenhouse warming so that the planet was warmer early on, and something happened. What we want to do is understand, where did the water go? Where did the carbon dioxide from an early thick atmosphere go? There are two places it can go. It can go down into the crust where it can get locked up, but we don't see the evidence for widespread, abundant carbon-bearing minerals in the abundance necessary to be a reservoir for that thick early atmosphere. The other place these could have gone is up to the top of the atmosphere, where they could be stripped away and lost to space. The removal process would involve forcing by the sun from solar wind, from solar extreme ultraviolet photons, from light waves, from solar storms that might strip away gas from the top of the atmosphere. MAVEN is all about trying to understand these loss processes, understand what could have happened at the top of the atmosphere and how gas could have been removed from it. Now, we can't go back and study what happened over 4 billion years, but we can go and look at how these processes are operating today and how they might have changed, how the processes might have changed over time, and what the integrated effect would have been. Can we go to the first graphic, please? We've selected 8 instruments, 9 sensors, so there are 9 boxes here, to make the measurements. We want to understand all the different connections in the chain, from the energetic drivers to the response of the structure and composition of the upper atmosphere to the escape to space. In the upper left on the chart here, you see 4 instruments that are focused on measuring the energetic input from the sun, the properties of the solar wind as it hits the atmosphere, the solar extreme ultraviolet light waves, and the solar storms. Each one of these is capable of driving processes that can lead to escape. In the lower left, you see the instruments that are going to be measuring the properties of the ionosphere. The ions are created when solar light strips an electron off of an atom or a molecule, and the ions have a specific set of processes that can lead to escape, and we want to understand what those were. In the lower right, you see the instruments that measure the basic composition and structure of the upper atmosphere today and tell us about the things that can lead to escape. With these 9 sensors, we're able to make all of the measurements that we need in order to understand what role has been played by escape to space. If you go back to the graphic, please, I also wanted to focus on the spacecraft here. The instruments are arrayed around the spacecraft, each one able to make the measurements that it needs at the same time so that we can get measurements throughout the orbit. The instruments are at the end of the solar panels, at the end of booms, or an articulated platform at the bottom so that they can be oriented relative to the planet. The spacecraft is in an elliptical orbit around the planet designed to allow us to make these measurements. It goes from the lowest point in the orbit, about 150 kilometers altitude, up to 6,000 kilometers. From the high point, we can make observations of the whole planet, and we pass through the upper atmosphere on every orbit. In addition, 5 times during the mission, we're going to lower that lowest point to 125 kilometers, and that lets us sample the entire upper atmosphere, all the way down to the well-mixed part where it connects to the lower atmosphere, and all the way up to the top where it connects to the solar wind. Even though we're passing through the atmosphere, it's so tenuous that it just doesn't create much drag on the spacecraft. We'll feel it, but it's not going to affect our orbit very much. We're going to hear from the rest of the panelists, from the deputy PI who's going to talk about some of the processes, and we have 3 of the instrument leads to talk about how the measurements will let us go to this question of how much gas has escaped over time So I'll turn it back to you, George.
All right, thank you, Bruce. We'll talk now with Janet Lumen, the MAVEN Deputy Principal Investigator from the University of California at Berkeley. Janet?
Thank you, George. If we can start with my first video. The sun is a major player in this mission, as Bruce has said. The Earth is thought to have had its atmosphere protected somewhat by its magnetic bubble of a relatively strong internal field, but Mars only has very localized remnant magnetic fields that form small umbrellas of protection, so that the atmosphere is more or less exposed most everywhere to the onslaught, the direct onslaught of what's coming from the sun. May I have the next slide, please? This is an illustration, a very complicated one, of what we think the various processes at work are in removing the atmosphere of Mars at the current time, and presumably throughout the history of Mars since it settled down from its initial formation phases. What we find is that it's a hugely complex system with a lot of inputs and outputs. The sun is producing, in addition to the radiation, the photons. It's producing these gusts of solar wind called coronal mass ejections. It's producing energetic particles. And Mars is responding in various ways, literally bristling with loss processes. MAVEN is instrumented specifically to be able to measure what's coming in and what's going out, and how the output responds to the input. This will allow us to estimate over long time periods, the order of billions of years, which is the age of the solar system, how long Mars has been exposed to this kind of loss process, and therefore how much atmosphere could have been removed in this way. May I have the next video, please? We are fortunate that the sun has been predictive in some sense. We are going to be arriving at Mars at the time of the blue arrow next September. And the sun, even though the sunspot number has been fairly modest by standards, previous standards in the space age, the sun has been quite productive of these conditions that you see on the right in the Soho movie of coronal mass ejections, which is a very recent movie, giving you an idea of the fact that the sun is definitely not a quiet star at this time. We expect it to be active when MAVEN arrives, and we will be able to sense the arrival of these gusts of solar wind and all the associated particles and fields, and hopefully understand the response of Mars. The early sun was supposedly more active than the current sun, and so we expect that these active periods that we're seeing in the solar maximum will better represent the history of Mars, the early history of Mars, for our purposes of going back in time. And I will pass it back to you, George.
All right, thank you, Janet. And now to begin our discussion of the instruments, Nick Schneider, the MAVEN IUVS instrument lead from the Laboratory for Atmospheric and Space Physics at the University of Colorado at Boulder. Nick?
Thank you, George. MAVEN has two instruments on board that measure the composition and structure of the Mars atmosphere, and those instruments are the imaging ultraviolet spectrograph that I lead and the neutral gas ion mass spectrometer that you'll hear about next. And these instruments operate in very different ways, but they provide complementary information. So I'll talk about how we figure out what's in the atmosphere and how it's distributed around the planet, how and why we make those measurements, and I'll be emphasizing the imaging ultraviolet spectrograph. So our instrument takes advantage of the fact that the entire atmosphere is glowing at ultraviolet wavelengths. And the graphic will explain how we can take advantage of that glow in order to understand where what the atmosphere is made of. If you could bring up that graphic. If you run electricity through a tube of gas, it glows. This is the principle behind fluorescent lights and neon signs. And the example that you see in the graphic is a tube of hydrogen gas. And to the eye, it glows pink. But if you spread that light out by looking through a prism or running it through an instrument like ours, what you see is not the full rainbow of colors, but just the specific at specific wavelengths of light, and that is the spectroscopic signature. It's the fingerprint of hydrogen gas, and every gas has its own unique fingerprint, so even from a distance, when we take a spectrum of it, we know what gases are there. So wherever we look with our instrument, we can figure out how much carbon dioxide, how much oxygen, how much hydrogen there is, even off at a distance. Let me show you how this plays out in flight. And this is a model of the MAVEN spacecraft. It's about 30 times smaller than the actual spacecraft. And normally the spacecraft keeps the solar cells and instruments oriented towards the sun. So any instrument that we want to study the planet is mounted down here on this movable platform. So whichever way the spacecraft has to move in its orbit, and whichever way the spacecraft needs to be oriented, we can ensure the proper direction for our observations. Now, I think of NGIMS as the nose of the spacecraft. It's right here, and as we skim down through the upper layers of the atmosphere, NGIMS is basically sniffing atom by atom, molecule by molecule to figure out what the composition of the atmosphere is right at the location of the spacecraft. Now, at the same time, our instrument is looking off to the side in the distance at the glowing atmosphere. And not only can we look in a single direction, but we have a moving mirror that allows us to scan up and down and see the composition of the atmosphere as a function of altitude. And at times when we're far from the spacecraft, we can actually map out those ingredients over the whole globe of the planet. If I can hand that over to you. Thanks. Careful. Got it. The reason we're studying the composition and structure of the atmosphere is it reveals to us how much energy the atmosphere is receiving from the sun. And at times when there's excess energy input in the form of those harsh ultraviolet photons or particles from the solar wind, it has a number of effects on the atmosphere. And the first thing that it does is it puffs up the atmosphere. That extra energy heats it up, and we can measure that with our instruments. And the second thing that happens is that that excess energy causes chemical reactions, and it can break apart molecules, and it can strip the electrons off of atoms and create ions. We can measure all of that. The excess energy in all these forms also causes extra atmospheric escape. And so as we're making these measurements, studying the properties of the atmosphere, we're very sensitive to how the input conditions are leading to atmospheric escape. Now, we'll be paying very close attention at the times that Janet referred to of high solar activity, because those are the times most representative of the early sun. And so when we're measuring the escape rates during periods of high solar activity, that's our best guess about how much atmospheric escape was occurring billions of years ago. And we add up that level of atmospheric escape over time, we'll have a good sense of just how much atmosphere Mars lost through escape to space. Back to you, George.
All right, thank you, Nick. Now to Paul Mahaffey, the MAVEN NGIMS instrument lead from NASA's Goddard Space Flight Center in Greenbelt, Maryland. Paul?
Thanks, George. Delighted to support the mission with the provision of the mass spectrometer to study the upper atmosphere, physics and chemistry to contribute to the study of atmospheric loss in the current time, and then ultimately to contribute to our understanding of ancient Mars, ancient climate, and the habitability conditions on ancient Mars. As Nick mentioned, we're kind of the nose of the mission. We have a mass spectrometer that as we go down in orbit to the lower altitudes, primarily below 500 kilometers, we measure both neutral gas. I'll illustrate how we do that in just a second. And then we also sample gases that are ions already in the atmosphere that solar radiation has produced. And so we sample those both over the entire mass range of about 2 to 150 Daltons to see what we get, but we focus in on particular species that we believe are there that we want to get a higher spatial resolution with. Bruce selected an instrument payload that was very complementary. As Nick mentioned, the UVS kind of gets the global view. It'll be measuring things like carbon dioxide and molecular nitrogen, atomic oxygen, and so on, and very much get a global view over the planet, whereas we pretty much get a very detailed view, but just along the spacecraft track. So we'll be making measurements on every orbit as we dip into the atmosphere, and during these periods of the mission where we do the deep dips, we'll get even more signal going down to the point where the atmosphere is well mixed. We're also very complementary to the fields and particle suite of instruments. For example, the static instrument measures a range of energies of ions up to very high energies, and we measure the composition of ions as well at lower altitudes, but at the lower energies. So the UVS, the static experiment, and the mass spectrometer all complement each other very nicely. We're interested particularly in how the spatial distribution of these atoms and molecules changes with altitude, and that really ties to these processes of atmospheric escape. Let me give you one example. We have, for example, with the Curiosity rover, measured a suite of atoms and molecules in the well-mixed atmosphere, and one atomic species that's particularly interesting is argon. The primordial isotopes of argon are argon-36 and argon-38, and of course the 38 is a little bit heavier. The 36 is lighter, so it ends up going up higher in the atmosphere on average, and it escapes easier. So over billions and billions of years, you leave more of the heavy stuff in the atmosphere. And so we measure that both with surface landers, we've measured that with Curiosity, but we'll really get an idea of the distribution of these things in the upper atmosphere with our MAVEN NGIMS experiment. So I have to show a picture of the instrument developed by our talented engineering team at Goddard. What you see on the left is actually a protective cap for a break-off. When we get into orbit around Mars, we'll fire a pyrotechnic, that cap will come flying off and eventually land on Mars. But then the ionization source of the mass spectrometer will be exposed. And on the second graphic, I'll just remake the point that, we're down on the surface with our rovers, with Opportunity now roving on one part of the planet, and Curiosity shown in the left graphic on the left. And the study of Mars really is a program. You need to look at things both in detail on the surface and understand what's happening with the upper atmosphere to really get at the history of the planet. And so, in fact, we have a mass spectrometer on Curiosity. It's in the SAM suite. And the advantage of being on the surface is we can not only look at gases that were trapped in an ancient environment that we released by heating, but we can measure the current atmosphere very, very carefully and with high precision. So, for example, in that argon isotope measurement that I just described, we were able to get a very precise ratio of argon-36 to 38. It turns out to be about 4.2, very precise number. And that's really different than any place else we know of in the solar system. And these are primordial argon isotopes, and that's just really a signature of the lighter argon having escaped over billions of years easier than the heavier argon. And so we'll be looking at a range of isotopes and chemistries that go on in the upper atmosphere with our MAVEN mass spectrometer as well. So what I'll end up with is just a little bit of a snapshot with a video which you can look at now of how the mass spectrometer works. So this is basically a metal case, and what you see here is an electron beam, an illustration of electron beam that's ionizing the neutral gas in this case. It sees a molecule in the beam, it breaks it apart, it creates an ion from a neutral gas. That ion then gets focused into a quadrupole filter. It's a set of 4 rods, and as the ions spiral down the rods, they get separated out by mass. They hit a detector, you count the number of ions that come through at a particular mass, and you have what's called a mass spectrum. And that's how we measure the composition of the upper atmosphere. So that's how our instrument NGIMS works, and with that we'll pass it back to George.
All right, thank you, Paul. And following on to complete our discussion of the instruments is David L. Mitchell, the MAVEN SWIA instrument lead from the University of California at Berkeley. David?
Thank you, George.
I'm going to talk about just a couple of the processes that Janet showed on her complicated graphic. In the simplest terms, an atmospheric species at Mars has to attain escape velocity to leave the planet. For neutrals, this can occur via exothermic chemical reactions in the atmosphere and also by impact by energetic ions. May I have the first graphic, please? For ions, on the other hand, these are charged particles, and so they can be accelerated by electric fields arising from the interaction of the solar wind with the Martian ionosphere and with its crustal magnetic fields. However, these same crustal magnetic fields can form closed loops and trap the plasma on these closed loops so that it cannot escape. Nearby magnetic field lines are open to the solar wind, and they allow ionospheric ions to go out into space and be lost. This is a two-way street. It also allows the solar wind plasma to precipitate down and heat the ionosphere below. On MAVEN, we'd like the formation of these regions of open field lines are analogous to auroral zones on Earth. And it's a dynamic process, and they open and close as the planet rotates and as the solar wind magnetic field changes strength and polarity. On MAVEN, the SWIA and the MAG instruments are designed to map out the crustal magnetic fields and determine whether or not they're open and closed. The magnetometer measures the field's strength and direction, and SWIA measures electrons flowing along that field line to determine whether or not the field is open or closed. And this sets the stage for the interpretation of all the plasma measurements on MAVEN. However, this is a region with strong crustal magnetic fields, and Mars does not have strong crustal magnetic fields over the entire surface. There are large regions, particularly in the northern hemisphere, where there are very negligible crustal magnetic fields. And in these regions, the solar wind is able to interact directly with the Martian ionosphere. One of the key regions for ion loss is the interface between the solar wind and the top of the ionosphere. In this region, the ion density is relatively high, and acceleration to escape velocity can lead to significant ionospheric loss. If you could please start the video. Here, we see a simulation of ion loss from the top of the ionosphere at Mars. You actually see two processes at work here. At high altitudes, there's direct pickup by that solar wind as it flows past the planet. Those are illustrated by the white arrows that are shimmying around. Of interest here is the plasma instabilities that arise at the solar wind ionosphere interface, and you can see those at the bottom where large portions of the upper ionosphere are literally stripped away and carried downstream of the planet. So on MAVEN, we have a suite of instruments that are designed to study this interface in detail. The SWIA instrument measures the flow of the solar wind as it passes by the planet. SWIA, MAG, and LPW study the structure of the interface. And STATIC measures the composition and velocity of ions as they leave the planet. So our goal here is to try to understand the importance of these kinds of processes to the overall loss of atmosphere at Mars. And with that, I will pass it back to you, George.
All right. Thank you, David. And we're ready now to take questions. Please give your name and affiliation when the microphone comes to you. Questions over here? All right, right here in the front.
Hi, I'm Miriam Kramer with Space.com. I'm wondering, the instruments I think are supposed to be turned on about 2 weeks into the flight, and I'm curious if there will be any measurements taken en route to Mars and what those measurements might be.
Let me start. We're going to turn the instruments on to check them out, make sure they survived the launch successfully. That's the primary focus of getting them on as soon as possible. Some of them will be taking measurements during the cruise phase. We'll be doing observations of the sun in order to compare with the Earth. And Nick, do you want to say something about observations of possible observations of Comet Ison?
Sure, I'd be happy to. If we launch on time and if the top priority of the trajectory correction and all the other checkouts go okay, we'll have the opportunity to use our ultraviolet imaging spectrograph on Comet ISON. Many of the same gases that are present in the Mars atmosphere are also present in comets. And so what an ideal opportunity for us to try out our instrument and do some good science along the way. We're crossing our fingers, of course, about the successful launch and successful checkout. But we should, if we have the time, get some really great observations in the ultraviolet of Comet ISON.
Bill?
Bill Horowitz, CBS. I'm not sure who to ask this to, but when we're talking about these methods or ways that the atmosphere gets stripped out, I'm a little unclear about how those work on Earth. Is the magnetic field the predominant thing that prevents that same sort of escape, or is, I don't know how much gas gets replenished in Earth's atmosphere from the geology. That's one question, was just comparing the two a little better to explain it.
Would you like me to take it? This is a subject of debate in the science community, in fact, whether the presence of a magnetic field does shield a planetary atmosphere. The workings of the escape, there is escape in both cases. The workings of the escape processes are different. In the Earth's case, for example, the magnetosphere takes the brunt of the solar wind impact, but some of the energy is channeled into the polar regions mainly. And so there's a focus of the energy that helps produce things like the aurora. And also geomagnetic storms can be produced by the impact of some of these coronal mass ejection pressure pulses. So there's energizations going on, but they're different kinds of energizations. And so the way it works in the Earth is that the energy gets into the polar regions, stirs up, heats the ions, and then they flow out of the polar cap. And then they have to make their way out of the magnetosphere. So even though there's an energy input and a heating process, it's focused into the high latitude regions. It heats, and the ions that are heated have to run the gauntlet to find paths out of the magnetosphere. However, estimates are that the current day escape rate for an important element such as oxygen and oxygen ions at the Earth is presently comparable to what's been measured at Mars by the Mars Express spacecraft and the earlier Phobos spacecraft. So current day rates of oxygen loss, anyway, are comparable. What we want to determine is whether the rates scale with solar inputs in a different way at Mars, where we have the direct interaction with the upper atmosphere rather than the filtering by the magnetosphere.
Thanks. One more quick one.
If I could follow up on the answer on that, I'd like to point out that one of the processes that Bruce mentioned was suspected at Mars has definitely occurred on Earth, and that's the absorption of atmospheric ingredients into the planet, into the crust itself. And so that's where most of the carbon dioxide given off by volcanoes has ended up on Earth. And so that process has definitely changed our atmosphere here. The other thing I wanted to emphasize, that even though we do know that atmospheric escape is happening from the Earth, there's no way that our atmosphere will lose the habitability of our planet. We have both a magnetic field and strong gravity. So it's a very different story for Mars in the past.
Thanks. And I don't know if you can answer this or not, is Mars today, would you guess, but I know that's part of the reason for the mission, but is it nearing a steady state? Is there some lower limit to where you wouldn't expect to lose a lot more and it would just stay there, or could you lose it all if enough time goes by?
What has happened on Mars is that the most intense loss is thought to have occurred early in the history when the sun, the solar wind were more intense. The loss rates today are low enough that we're probably not going to see the loss of the entire atmosphere. The reason we're studying it today, even though the loss rates are so much lower, is that we can understand the specific processes that are going on and learn how to extrapolate them backwards in time.
Do you have any additional comments you want to make on that, Michael? Okay. All right. Let's go right here.
Frank Mooring with Aviation Week. I think this is for Bruce. Nick mentioned that you're using some data or comparing some isotope data from Curiosity. I wonder, is there any specific coordination planned among the various spacecraft at Mars with MAVEN?
We are looking at coordination between the different spacecraft. The reason we need to do that, the reason we want to do that, is that Mars is actually a very complicated system. We've gone beyond the ability to look at one part of the planet and understand everything there is to know about it. The atmosphere connects to the upper atmosphere and to the solar wind and lost to space. It connects to the surface, the polar caps, the deep interior. So we need to understand all parts of it, and that requires comparing observations from different spacecraft. With Curiosity, as Paul mentioned, we're comparing the isotopes we're going to measure at the top with the isotopes at the bottom. We don't need to do any specific coordination because both spacecraft are going to be working, doing their own thing, and we can compare the data after the fact. Where we think we can do the most valuable coordination is with the European Space Agency Mars Express mission, because they have several instruments that are measuring things very closely related to the things we're measuring, and we want to make sure that we're getting the right observations at the right time to be able to do that cross-coordination. We have a working group made up of members of our team and members of their team for the specific purpose of doing that coordination. We've also approached the Indian space mission to Mars, Mangalyaan, in order to discuss whether there should be coordination there, because they also have a couple of instruments that make relevant measurements to what we're doing and vice versa. There we've agreed that after we're both in orbit taking data, we'll figure out what coordination we need. I'm suspecting that it'll be after the fact comparison of data rather than coordinating the observations, but we've agreed to look at that after we both get there.
Okay, Ken.
Hi, Ken Kramer for Universe Today and Rocket STEM Magazine. I'd like someone, maybe several of you, to talk about why you chose this particular elliptical orbit. I think the tenuous atmosphere is extremely more tenuous at the higher 6,000 kilometer altitude. So why did you pick this orbit? Why are we not having an elliptical orbit that's closer into the planet? When are these science instruments making their measurements? Is it mostly when we're at the lower orbit, or is it continuous throughout?
Let me take a start at that, and these guys can chime in as well. We picked the orbit for two reasons. One is with an elliptical orbit that goes as low as 150 with occasional deep dips down to 125, we get to sample the entire upper atmosphere. So the in situ measurements pass through the important parts of the atmosphere on every orbit. At the highest altitudes, the IUVS instrument can do imaging of the emission from the atmosphere to tell us about global composition. So that elliptical orbit with that low altitude and high altitude lets us get the measurements we need. We picked that particular orbit as well because the gravitational torquing from the planet will cause it to precess. The plane of the orbit will rotate with respect to the line from the sun, and that will let us get different local times relative to the sun. And it also precesses in latitude, so the latitude of periapsis, the closest approach to the planet, sweeps between plus and minus 75 degrees. So that gives us relatively complete coverage in all three dimensions. Throughout the orbit, we've divided it up into segments, and each instrument makes its measurements, makes its most important measurements at the altitude range that is most important to it. So IUVS and static focus on the high altitude parts. At the other end, the NGIMS instrument and static and IUVS focus on the low altitude parts, and everybody takes measurements in the middle. Everybody's taking measurements most of the time, but different altitudes provide different measurements that tell us about different aspects of the upper atmosphere. Nick or Paul in particular, do you want to add to that?
I do want to add to this. Bruce referred to how at great distances our instrument is able to make images of the planet and the atmospheric ingredients, but it's just as important on the times when we're rising up above the planet, we look sideways through the uppermost layers of the atmosphere. And when I say uppermost, I mean thousands of kilometers in altitude. So we are still detecting hydrogen and oxygen thousands of kilometers above the surface. Those being the ingredients of broken down water, this is really an essential part of solving the problem.
And, excuse me. And of course, the atmosphere gets denser and denser as you go down toward the well-mixed atmosphere. Interesting to note that we really don't have a lot of information in the deep atmosphere. Some of the current orbiters are focused primarily on remote sensing and spectroscopy and so on. And we have a couple of measurements way back from Viking. And, you know, they're kind of one-point measurements as the aeroshell went down into the atmosphere supporting the landers. There was some really interesting obtained, but we're really just going to get hundreds of these measurements over the course of the primary mission. So the orbit allows us to do that. It allows us to look at different local times and day-night variations, and then of course with the orbits look at how the atmosphere is changing, both with things that are happening on the surface like dust storms, the atmosphere is breathing in and out, and as a solar input to the atmosphere is changing. So that orbit really enables this repetitive look at the atmosphere that you need to study some of these processes.
I need to clarify part of my answer. I talked about the atmosphere going up thousands of kilometers. The technical term that we use is the exosphere because it's really, really thin, so thin that actually the atoms don't collide with each other. Nonetheless, our instruments have the sensitivity that we can actually measure that very rarefied gas.
I could add to the answer as well. The Particles and Field Suite is making measurements throughout the orbit. It's important to realize that we want to understand the sun as a driver. So as the solar wind changes, the velocity increases, as the density increases, how does the planet respond? And so when we see things happening in the solar wind, we're going to definitely try to make correlations with how the planet responds. So it's really important to make these high altitude measurements to make those connections. And so that's an important part of the MAVEN strategy.
Okay, we're going to stop and take a question on the phone, and then we'll come back here. Irene Klotz from Reuters.
Thanks very much, George. This question is for Bruce. I think last month you said that there'd be enough fuel aboard the spacecraft for 10 years, primarily to serve as a communications relay after the first year of science operations. And I was wondering if the orbit would be circularized to serve that communications relay function, and if so, how does it impact any additional science from a follow-on mission, or how are you going to kind of balance off the desire for additional science with the secondary role as a comm relay? Thanks.
Well, let me first clarify that we designed the spacecraft and the amount of fuel we carry to be sure we can accomplish our primary mission. So the amount of fuel was sized so that if we have problems getting into orbit, we can recover from that. We don't anticipate that, in which case the extra fuel we carry would be able to be used to extend our operations in orbit. If things go our way, we might be able to continue to operate for as long as 10 years. Of course, that remains to be seen. We'll find out as we go through the process. The first year primary mission, we've set up what we're going to do. We have enough fuel to continue making observations in the same mode if we don't need to correct our orbit after we go into orbit. We can continue observations in the same mode for about two more years. Then what we would have to do is raise our periapsis so that atmospheric drag becomes less of a factor. We wouldn't circularize our orbit, but we'd get the lowest part out of a little bit further out of the upper atmosphere to conserve fuel. And at that point, we'd be able to continue a combination of science observations and relay operations, perhaps out to the 10-year mark. I believe that relay and science can coexist, and we ought to be able to do both of those after the primary mission until through the whole lifetime of the spacecraft.
Okay, right here.
So maybe a quick follow-up then for Mike is with both MO and Global Surveyor getting on in years, what's the plan for comm relay for InSight and Mars 2020 if MAVEN's not taking on that dedicated role?
Yeah, as you correctly point out, the two main communication orbiters we have right now that are doing science are Odyssey and Mars Reconnaissance Orbiter, and they are getting long in the tooth, and we do have to plan for eventually when they're no longer operational. So this is a concern, and for this reason, every spacecraft that we send to the Red Planet, and even other nations who send a spacecraft to the planet, we ask them to carry a communication device so that there is the opportunity to communicate with on-the-surface assets through the orbiters. So the plan is the analysis has been done on what the expected lifetime is and what the probability of having one or two orbiters by the time we have InSight land on Mars, and then also when we send the 2020 rover. And we're okay, and we're using, basically, MAVEN will be a backup. Mars Express may still be going, and Mars Express has the capability of doing communications with the rovers. And so we're recognizing that our spacecraft are getting older, but we're having backups so that if need be, we can call on them to provide communications.
Right here.
Marie-Michelle Limoges, CBC and University of Montreal. I'd like to know if the models of the evolution of the sun are constrained well enough to allow us to study the impact of the sun on Mars's atmosphere.
That's a very good question. The history of the sun is one of the major outstanding problems of solar system exploration in the evolutionary area. And the observations of sun-like stars are fortunately getting better and better. And so people can appreciate that sun-like stars have cycles. And there's a pretty well-established trend of the extreme ultraviolet flux with time. They can tell how old a sun-like star is by its rotation rate. And so the astrophysics community and astronomy community have been focusing, part of that community has been focusing on sun-like stars and their evolution. An outstanding question remains the nature of their activity and whether the early activity that's implied by their higher extreme ultraviolet fluxes at an early age also implies a lot more coronal mass ejections and solar energetic particles and stronger solar wind gusts. So we hope to be doing our science in parallel with the astrophysics community, and as that further is further constrained by that research, we will combine the two banks of knowledge in a best guess of the outcome.
Right here.
Hi, Jeff Faust of Space Review. For Bruce or anyone else on the science team, you've been working on this project now for several years. It's the day before launch. How do you feel right now? Excited, nervous, something else?
All of the above. That several years is actually 10 years since we started putting together the original concept. And it really is all of the above. I don't know how to put into words what it feels like to be down to the day before launch. But I'll tell you, it was one of the most exciting things I've done to go out yesterday and watch the rollout to the pad and see the rocket and the spacecraft inside it come out of the integration facility that it had been stacked in, and to see the MAVEN logo on the side up here. I just don't have the words for it, but it's an incredible experience, and I recommend everybody should be a PI at some point.
I could add another perspective on this, missions like this usually start on the back of a napkin, and then they go to the back of the envelope and onto a whiteboard and PowerPoint, and before it's in the computer-aided design drawings, and it's got aluminum prototypes, and then they're wiring it up, and then they're shipping it, and here it is on the launch pad. And in a lot of ways, it's gone much faster than I thought, because there's this drumbeat of the progress that's necessary to get ready for launch. So it's been a great ride. Center received 27,000 MAVEN emails, and that sounds like a small fraction of what you've had.
Right, James?
Hi.
I'm sorry, James Dean right next to you there.
I'm sorry. James Dean, Florida today. In terms of habitability, I was just wondering if you could discuss a little more will your findings, is it about telling you more about what the atmosphere that used to be there was like, or is it more about perhaps just like framing the period during which the most habitable conditions would have been, or is it something else?
I see this mission as core an astrobiology mission, because one of the real intellectual drivers for Mars is understanding whether there was life or could have been life. And with the climate, why do we appear to have had a climate on Mars that could have supported life at the surface early on, and we don't today? You know, something fundamentally changed, and we want to understand what those changes were. So I really do see this as a mission about the history of Martian habitability, and of course habitability by microbes. If we think more broadly, we're understanding processes by which a planetary environment can change through time. We don't know the whole range of processes yet, but as we're starting to discover more and more planets outside our solar system and see Earth-like planets and ask about whether there could be life on those, we want to understand what makes a planet habitable and what makes a planet go from being habitable to not being habitable. So I see this as a much broader mission than just exploring the Mars upper atmosphere today and learning about the history of the climate, but that's where we start, because those are the questions that we get the first answer to.
Right here.
Thank you. Tony Rice, WRAL TV and social media, Mars WX report. Had a question about public engagement. Was curious what the plans were for data availability. Would there be an embargo? Would it go into the planetary data system as it normally does? And would there be any plans to engage the public with the meteorologic data that you're producing here, similar to the way the Curiosity rover has produced meteorologic data on a daily basis?
We will be making data available to the public, both the public at large and the non-science team science community, the rest of the science community. Our plan is to make it available as soon as possible. As you've heard described here, though, the data is not instantly easy to interpret. It comes in a form that requires some expertise, and that means that the individual instrument teams are going to need to take time to make sure they understand how the instruments are operating, what the calibration is, and that we've applied the calibration. The last thing we want to do is put out data that is hard to interpret or has to be corrected later when we better understand the calibration. By decree from NASA headquarters, there is no proprietary period, and we are obligated to put the data into the planetary data system as soon as it's available. And we have a schedule set up by which we will do that. So we're absolutely committed to making it available. My goal is to make the data as available to everybody as possible, because then we can really get a lot of people doing science with it.
Did you want to mention the other EPO activities on the mission?
Go ahead.
Okay. So, of course, we're also spending a fraction of the MAVEN budget on educational activities, things like teacher workshops. There's a great show to be projected on the Science on a Sphere displays. We expect to go national. A lot of attention to serving underrepresented communities in science.
Okay, a question right here.
Hi, Don Haladian for CBC. Question for Janet. In one of your graphics, you showed these isolated magnetic bubbles. Did Mars once then have a more extensive global magnetic field? And when did it break down, maybe allowing more atmosphere to be stripped away?
Yes, the Mars Global Surveyor mission first measured those crustal magnetic fields. And the crater record and other knowledge of the way magnetic fields and dynamos work has led the community to conclude that there was probably an early global dynamo of Mars with a stronger dipole field. And the dating suggests that it disappeared around the time of the atmosphere's disappearance at about 3.5 billion years of age or ago. So that we are examining the processes that started at about Mars being 1 billion years of age after the initial period of internal dynamo activity and strong magnetic field presence.
Okay, we'll take one final question from Bill Harwood, and that'll wrap us up.
Simple question. I'm sure it's in the press kit, but what is the data that comes back? What part of the orbit are you doing that? Is it continuous? How does it get back?
We are collecting the data on board and storing it on board. We'll send it back twice, once we're in orbit, once in our science mapping orbit. We'll send it back twice per week. You will have seen on the model of the spacecraft that the high gain antenna is body mounted, it's fixed. That means if we want to point at the Earth, we have to point the whole spacecraft, and that means we aren't making our complete set of measurements while we're sending data back to the Earth. So there's a trade-off between how often we want to do that and take away from the science measurements versus how much data we can send back. We've settled on twice a week.
All right, in that event, that's going to wrap things up. Just a couple of notes. The website is www.nasa.gov/MAVEN. Our launch coverage on NASA TV on Monday morning begins at 11 a.m. That coincides with the start of fueling of the Atlas V. And now we're going to show you, to conclude our activity this morning, our briefing, is an animation of the evolution of Mars as a wet planet and into a dry planet that explains somewhat about Mars evolution. And thank you very much for coming.
15.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Main engine start, ignition, and liftoff of the Atlas V with MAVEN, looking for clues about the evolution of Mars through its atmosphere.
Control. Mark. Everything looking good. Still at 100% rated thrust on the RD-180. Vehicle rates are looking good. We do have roll.
And good afternoon, everyone. Welcome to the post-launch news conference for the MAVEN mission. Here to discuss how the launch has gone and the state of health of the MAVEN spacecraft, we have David Mitchell, the NASA MAVEN project manager from the Goddard Space Flight Center, Bruce Joukowsky, the MAVEN principal investigator from the Laboratory for Atmospheric and Space Physics at the University of Colorado at Boulder, and Dr. Jim Green, the director of the Planetary Science Division at NASA headquarters. And we'll begin first with David Mitchell.
Well, good afternoon, folks. What a Monday at the office. You know, you build something to go to Mars, and we're now flying at Mars today. So it's, maybe I'm not showing it, but I'm euphoric. I mean, it's been great, guys. So you know, what an effort by this team to get to this point. And so many years ago we started, actually Bruce 10 years ago started down this path. And 5 years ago, we put in the final proposal, and we put November 18th, 2013 as our planned launch date, and we hit it. So, and it's, so far, I'll talk about the systems in a minute, but so far, so good. So I'm really excited about that. So today, the countdown went really smooth. You know, it was actually very quiet, which is the kind of countdowns I love. So all went well on that front. And we did hit the opening of the window right at. I'm gonna go into UTC time. So liftoff was right at 1828. So that all went well. After we lifted off, from a spacecraft standpoint, we had a test control center down here at the Kennedy Space Center, staffed by our engineers, and they did all the countdown portion of it. And then after liftoff, from a spacecraft standpoint, it was handed over to the operations center in Denver. The Lockheed Martin organization out there is now flying this mission to Mars. So we've got teams here. We got them over there in Denver, and so far so good. So I'm going to read from a script, which is simply the timeline of what happened and where we are. So again, liftoff was at 1828. We separated from the Centaur at 1920. And 44 seconds, locked up on the telemetry at 1921 and 40 seconds. We confirmed system initialization, and tip-off rates were damped prior to initiating the solar array deployment. So that prop initialization was confirmed at 1926, and then we went ahead and deployed the solar arrays, and there was confirmed good collection, good data